So here is what we know about equilibrium. We first know that concentration or quantity plays a huge role in equilibrium. And we know that while the concentrations of the reactants don't have to equal the products, we do know that the concentrations have to remain the same in order for equilibrium to exist. So we have the same quantities of reactants and products and each individual reactant and product at equilibrium. Now, the reaction isn't stopped. The reaction is still going at equilibrium, but the concentrations remain the same. The next thing that we have to understand and know about equilibrium is that the rate is what stays the same. The rate of the forward reaction, so the rate of the creation of products should be equal to the rate of the creation of reactants. So the rate of the forward and reverse reactions have to be the same. So as far as rate is concerned, we know that once equilibrium is established, the rate stays the same. But what can we say about the concentrations? So we know that they remain the same, but can we know and can we tell what those concentrations of reactants and products are? And that's what we're going to spend this lesson talking about, or at least introducing. So let's take a look at this analogy of sunbathers and swimmers. Say we go to a pool and it's a hot, sunny day. It's 95 degrees Fahrenheit, and it's just one of those days you want to be in the pool. But what happens is when the pool opens, we start with a whole bunch of sunbathers, and eventually we get more and more and more swimmers. So those sunbathers decide, all right, I'm warm enough, I'm going to go in the pool and cool off. And then we have this back and forth happening. And initially we have more sunbathers turning into swimmers, but finally we get to this point where the rate of swimmers turning into sunbathers is equal to the rate of sunbathers turning into swimmers. So for every one person that gets out of the pool, one person goes into the pool. Once we see this, we know that we have established equilibrium. So we're going to change our arrow. Instead of an arrow moving in the just one direction, we're going to change it to a double-sided arrow. And we're going to say, all right, this is, now we've reached equilibrium. And if we were to really show equilibrium, I would continue showing the animations of one person getting out and one person getting in. But I'm going to stop that right now and just kind of take a pause of this reaction at equilibrium. So we're pausing this reaction at equilibrium, and we have 6 swimmers and 6 sunbathers. One thing we can do is we can show the relationship or the quantity or the ratio of swimmers to sunbathers. So we're going to show this by saying, okay, we have 6 swimmers for every 6 sunbathers. That's a ratio of 6 to 6, or 1. We are going to call this a constant. We're going to call this the equilibrium constant, or K. And this is 1, the equilibrium constant for this reaction at 95 degrees Fahrenheit. We're going to take a look at a cooler day and just compare. So this is a cooler day. We have 75 degrees Fahrenheit. It's a little bit cloudy. Maybe not as many people want to go in the pool. But let's take a look at the reaction. So we have sunbathers and swimmers. Now, initially, when we start the reaction, there will be all sunbathers. And when a few people warm up and they decide, oh, I want to go in the pool to cool off, some people start going in the pool. But now you'll notice that we have fewer people in the pool. Even though we have one person getting out for every one person going in, we've established equilibrium. This equilibrium looks a little bit different. So let's take a look at the new equilibrium constant at this cooler temperature. So we know we have equilibrium because we have the same number of people getting out of the pool as we have going into the pool. So the numbers are staying the same, and they're staying at 9 and 3. So the equilibrium concentration of sunbathers is 9, and the equilibrium concentration of swimmers is 3. So if we use the same ratio that we used before of swimmers to sunbathers, we now have a 3 to 9 ratio, or 0.33, as our constant. Now, like I said, we're going to call this K. We're going to call this our equilibrium constant. And the equilibrium constant is only good at specific temperatures. So at 75 degrees Fahrenheit, we have a different equilibrium constant than we have at 95 degrees Fahrenheit. So what can we use to represent the equilibrium constant of any reaction? Say we have this generic reaction of we have reactants on the left and products on the right, and we want to find the equilibrium constant as it pertains to concentrations. That's going to be Kc. So to do this, we need to take C, or the concentration of C, raised to the power of whatever the coefficient of C is. So I'm going to call that lowercase c, or the coefficient of C. We're going to multiply that by the other product, the concentration of the other product, raised to the power of the coefficient of that other product. And we're going to take this all over the concentration of one of the reactants raised to the power of that reactant times the concentration of the other reactant, if there is one, raised to the power of that other reactant. So this is how we would take a general or generic chemical equation and turn it into an equilibrium constant expression. Now, if we're dealing with not concentrations but pressures, say we have gases, then we would do the exact same thing, except instead of concentration, we would use the partial pressure. So the partial pressure of one of the products raised to the power of its coefficient times the partial pressure of another product raised to the power of its coefficient, all over the partial pressure of a reactant raised to the power of its coefficient times the partial pressure of another reactant to the power of its coefficient. So what does this all mean? Well, if we have a K value that's less than 1, this was the example of the cooler day, then the equilibrium will favor the reactants, meaning there will be more reactants than products. If we have K equal to 1, the equilibrium will equally favor the reactants and products. And if our K is greater than 1, then we will have more products than we have reactants. So when K is less than 1, that was an example of our cooler day. And when K was equal to 1, we had 6 over 6. That was kind of equivalent to our hot day. We had equal numbers of reactants and products. If we had a day that was so hot that no people would be sunbathing, then we would have a K way greater than 1. Okay, so up to this point, we've been dealing with K values that pertained to concentrations. And by the way, concentrations are measured in moles per liter. And we've also dealt with K values that included partial pressures. And partial pressures we would probably measure in atmosphere or another pressure unit. What if we're dealing with a solid that doesn't have either a concentration or a pressure? Solid particles don't exert a pressure on its container, so we can actually leave those out of the expression. We can also leave liquids out of the expression. Liquids aren't going to have a certain concentration. They're not solutions. They're just liquids. They're a molecular compound that's a liquid, or an element that's a liquid. They don't exert pressure, and they are left out of the equilibrium constant expression. So it's important to know the state of matter. If you have an aqueous solution, then we can use the concentration. If we have a gas, we can use the partial pressure. If we have a solid or liquid, we just ignore those in our equilibrium constant expression. And the reason we could ignore those is because solids and liquids do not exert pressure and they don't have concentrations. So let's do some practice problems where we write the equilibrium constant expression for specific balanced equations. I'm going to first write out the combustion of propane. Now, it's really important that we include the states of matter in this because remember, solids and liquids get left out of our equilibrium constant expressions. So this one has propane being combusted in the presence of oxygen. We'll say that the propane is a gas and the oxygen is gas, and it's going to produce carbon dioxide gas and water in the form of a gas, so steam, just because usually combustion reactions produce water in the gas form because they're so hot that the water is in its gas form. If we balance this, we get 1 mole of propane for every 5 moles of oxygen. and that creates 3 moles of carbon dioxide and 4 moles of water. If we're writing the equilibrium constant expression for this, we're going to include the partial pressure of the carbon dioxide as the numerator, and we're going to raise that to the 3rd power because that's the coefficient on the carbon dioxide. The partial pressure times the partial pressure of the water to the 4th power, and then that's all going to be over the partial pressure of the propane to the 1st power because the coefficient is 1 times the partial pressure of the oxygen to the 5th power because the coefficient of oxygen is 5. So this is our equilibrium constant expression. Let's take a look at another example. In this example, we have a solid aluminum chloride that's being formed from solid aluminum and chlorine gas. So I'm going to write this reaction out, including the states of matter that each chemical is in. So I have aluminum in solid form plus chlorine gas gives us aluminum chloride in solid form. Now I need to balance this. So I'm going to put a 3 in front of the Cl2 and a 2 in front of the AlCl3 and a 2 in front of the aluminum. So my equilibrium constant expression is only going to include the chlorine gas. Remember, solids and liquids get left out. So if it gets left out and there's nothing to be the numerator, then 1 will be our numerator, and the partial pressure of the chlorine gas raised to the 3rd power is our denominator. The last problem here, the reaction between aqueous calcium chloride and sodium hydroxide. So for this problem, we need our solubility rules. So we have calcium chloride, which is soluble, so it's aqueous, plus sodium hydroxide, which is soluble, so that's aqueous. And then this is a double replacement reaction producing calcium hydroxide, which is not soluble, so that gets a little solid symbol, and sodium chloride, which is soluble, so that gets a little AQ. We're only going to include the AQs in our equilibrium constant expression. And now, because we have aqueous solutions, our equilibrium constant expression is going to be K sub C, because we will be dealing with concentrations of solutions rather than partial pressure of gases. So Kc is going to equal the concentration of the sodium chloride raised to the 2nd power. We're going to leave out the calcium hydroxide because that's a solid. We don't need that. That's going to be not part of our constant expression. And then what we get is, on the denominator side of it, we get calcium chloride times sodium hydroxide to the 2nd power. So this is the equilibrium constant expression for that double replacement precipitation reaction.